Okay, so in this lesson, we're going to learn something called the normal force. Now, the normal force is a very important concept to understand in physics. It's going to help you solve a lot of complex problems in dynamics. And yeah, it's something I don't love the name of it, that they call it the normal force, but that's what it's called. And that's how we're going to talk about it. And I'll explain to you exactly what it is. So you've got your lesson sheet out, and what you'll see at the very top here says, the normal force is a reaction force, and it's perpendicular, and that's where the word normal comes from. It's not normal because it's normal, like it's just a normal force, although it does exist everywhere. The reason it's called normal is because of the word perpendicular. So a angle that is normal, or an object that is normal to something else, means that it is at a right angle to it, or 90 degrees. And that's what the word perpendicular and normal means. So it's a 90-degree contact force. And whatever force or whatever surface you're touching, there is this reaction force of the surface on the object that is at 90 degrees to that surface. So what does that mean? Well, you can think about it this way, and there's lots of different ways of thinking about it. But if you push on a wall, if you really think about it, it feels like the wall is pushing back on you. And that sounds like something called Newton's third law. And in fact, the normal force comes about because of Newton's third law. So if you push on a wall, it feels like the wall is pushing back on you. The key is that the force that you're pushing and the perpendicular normal force or reaction force, they're balanced out. They're the same amount of force, but pointing in opposite directions. So another way to think about it, and we'll use this example of Vector the elephant standing on a scale. If you're standing on the floor, you know that you have weight. You have mass times gravity pulling you down. You are attracted to the earth, it's pulling you downwards. So let's say in the second floor of your house and you're standing um, on the floor, you're not accelerating. And if the only force acting on you was the force of gravity, m times g, you would accelerate through the floor at 9.8 meters per second towards the ground or towards whatever's below you. That doesn't happen. And that's because the ground or the floor is pushing up on you with an equal force called the normal force. It's perpendicular to the surface. So if you're standing on the ground and you're applying a force of 700 newtons to the floor is pushing up on you with 700 newtons of force. That means an upward force of 700, a downward force of 700 acting on your body is balanced, so you don't accelerate. Newton's second law says sigma F equals ma, or net force equals ma, and therefore you are not accelerating. The acceleration is zero because the forces are balanced. And that's another way to start to realize, oh, there's forces, these normal forces acting on objects all the time. Depending on the angle of the surface, it doesn't matter. Whatever you're touching or whatever object is touching, there's a perpendicular force acting on it. And it's always 90 degrees to the surface it's in contact with. And the normal force is a reaction force. It's based on Newton's third law. So let's consider Vector the elephant. He's a mass of 1,000 kilograms. He's standing on a scale. He's being pulled downward by gravity. Calculate his weight in newtons. So here's Vector the elephant standing on this scale. We're going to draw his free body diagram over here. He has a mass of 1,000 kilograms. And we're going to take a look. So we draw this here. And we know that this is Fg. Now, you could write Fg equals mg. A lot of people just write it as mg. And what you would do is you would take 1,000, which is his mass, and then you would simply multiply it by 9.8 on Earth, and you would get 9,800 newtons of force pulling down on this object. Now, what I like to do, if I know that this object is touching the surface, I like to draw a surface. Okay? You don't have to, but I like to do it just so I remember. I don't write the word surface, but I just remember, oh, okay, he's touching the surface. Now, if this was the only force acting on this elephant, he would accelerate down to the ground at 9.8 meters per second, picking up 36 kilometers per hour of speed every second that goes by. He's going to rip through everything, just accelerate down. That's not happening. He's standing on a scale. So there must be a reaction force, F subscript n. That is the normal force. So the F subscript n is called the normal force. Notice it is perpendicular. It's 90 degrees to the surface in contact. Now, what you would notice here, and this is a big concept to understand, that the normal force is equal to the scale reading. So at any point in time, if you are standing on a scale or there is a force meter that you're standing on, whatever that scale reads is the exact value of the normal force acting on you. Okay. Even if you accelerate, if you push off the scale or you jump onto the scale, it doesn't matter. Whatever that scale reads, that is what the normal force is on that object. And that's a really cool thing to think about. So whenever someone says, what's the scale reading? They're measuring the normal force. It is a force. It's not necessarily your weight, because you could jump onto the scale and the scale will read a lot higher. Well, the reason it's reading higher is because there's a normal force that's bigger than gravity, which is slowing you down and causes you to decelerate. If you accelerate up, the normal force is bigger because you're accelerating up. If you're standing stationary on the object, then the normal force is equal to the weight of the object. Okay? So this, remember, is the weight of the object. So in the very specific case of no acceleration, in this very specific case of no acceleration, the normal force will exactly equal the weight because you're not accelerating. Okay, how do we get this further? How do we look at this a little bit better? If we do this and we write sigma F equals ma, and we say, listen, the object is not accelerating, so it's balanced, and we've done this a million times, then the net force equals 0. Well, if we choose, let's say, up to be positive, then we know it's Fn minus mg, which equals 0, and you end up with Fn equals mg, equal to the weight. There you go. Now, this is, the big caveat, the big warning here, this is not always true. This is fake news if you think that, oh, Fn is always equal to mg. It is not, very rarely. Like in only static situations where objects are at rest on objects, on surfaces, is that ever true. And if it's on an angle, it's not even true. If it's on an angle, there's like, you have to include sine theta in here and some like components and all this sort of stuff. This is a very specific case. I need you to understand that. I don't want to lead you down this path of you thinking that, oh, whatever the weight is, that's what the normal force is. It's not true. It's only true for very, very specific cases. So keep that in mind. Okay, it's really, really important. Okay, what we're going to look at here, some sample problems, is we've got Vector Delphin standing on a scale. He's holding a helium balloon. Here, the balloon pulls upwards with a force of 200 newtons. What is the reading on the scale? Notice how I put this. The reading on the scale, which is the normal force. Okay, so if the balloons are pulling up, do you think his weight is going to appear bigger, or is it going to appear smaller? Okay, I think probably most of you would have thought, okay, well, it's pulling up, so this is going to appear lighter. So his normal force should be smaller. Well, let's see. If we draw the free body diagram, his 1,000 kilogram mass, I'll just make him a square, whatever. We know that the force of gravity pulling down is mg, which equals 9,800 newtons. That didn't change. But now there's a balloon force. That's F subscript B, and the balloon force is 200 newtons. Okay, well, there's a surface. Is the object accelerating up or accelerating down? No, stationary on here. So we know that the forces are balanced. Okay, well, if we choose up as positive, then we would say, oh, wait a second, this isn't balanced. This thing is accelerating through the ground like crazy, but it's not because you must include the normal force. So now if you look at it, the normal force plus the balloon force minus the weight must be 0. So the normal force is going to be the weight minus the force of the balloon. 9,800 newtons less 200 newtons equals 9,600 newtons is what the normal force is. And you can check it. 9,600 plus 200 is 9,800. It balances, it's not accelerating, that's the situation. So notice how the normal force dropped a little bit because you're not in contact with the surface as much. Drawing the free body diagram is important. Writing out Newton's second law is super important. And then solving for the normal force. So notice here, normal force is not equal to weight. It's a little bit less than the weight. And that's why this caveat up here is extremely, extremely, extremely important to understand. Okay, let's look at the next part. Okay, now Vector the elephant is holding 2 identical balloons. What is the reading on the scale? So what will the normal force be? Well, if he's holding 2 identical, you would guess right away. You'd be like, well, it's going to be 9,400 newtons. Okay, so let's do a quick little thing. 1,000, and then leave a lot of space here. 9,800 newtons of gravity. There's now 2 balloons and a normal force. The net force is still 0. We'll pick upwards to be our positive direction. And you would then say, well, okay, the normal force plus 2 times the force of the balloon, because there's 2 of them, it's just faster to write that, less the weight equals 0. So the normal force is going to be equal to the weight less the balloon forces. And you're like, this is a lot of work to get to an answer we know is easy. And 9,800 less 400 is 9,400 newtons. And again, you almost don't need to do all this Newton's second law stuff, but do it anyways for practice in case the questions get harder. You would just look at it and say, well, that's 200 and 200, and I have to equal 980, so that's got to be 9,400. Done. You could do it without any of this sort of strict mathematics, but again, I would urge you to try it. How many balloons would Vector the elephant need? So the reading would be 0. Oh, that's an interesting problem. So let's say that we've got Vector the elephant, 1,000 kilograms, standing on this scale. And we know the weight pulling down, the mg, has not changed. It's still 9,800 newtons. And now there's a whole bunch of balloons. So I'm just going to call it F. It's a whole bunch of balloons. I don't want to write them all down. And you look at it and say, well, it says the scale should be 0. So that means there should be no normal force. Well, the only way this happens is if you just lift off the surface, so you're not in contact with the surface anymore. Well, Newton's second law still holds, but it's still balanced. You're just lost contact with the ground. There is no normal force, so we don't even include it in here. And we have a certain number of balloons, we don't know how many, minus the weight equals 0. And so however many balloons there are, it must balance the weight. So to find n, we just take whatever the weight of the balloon, the force of each balloon. So that was 9,800 newtons divided by the force each balloon supplies. And so you just do 9,800 divided by 200, and you get 49 balloons. So if you attached 49 balloons to Vector the elephant, that would match his weight, and therefore he would just lose contact with the surface, giving him a normal force of 0. Okay, you could put an NF here just to say the number of balloons, but I didn't want to draw 49 balloons on there. I guess you could write it like this, NFB, for N standing for the number of balloons. All right, what if you picked up one more balloon? So now he's got 50 balloons. His weight has not changed. Gravity is still pulling down on him with 9,800 newtons. But now the upward force pulling from these balloons is 50 times 200, which is 10,000 newtons. Notice something? There's 10,000 newtons pulling up, only 9,800 pulling downward. Therefore, this guy is now in an accelerated phase. It's now accelerating away from the ground. So when we write sigma F equals ma, or Newton's second law, a is no longer 0. So we made up positive in the direction of the balloons, which is important. So F minus mg equals ma. And so the acceleration was whatever the upwards force is, less the gravity, divided by the mass. And you get 10,000 less 9,800 all over 1,000. And so really the net force is just 200 newtons. That's the difference between that. That one balloon just added that extra 200. And you get 0.2 meters per second. And that's it. So it's a very slow upward acceleration by adding that one extra little balloon. Okay, back to the elephant standing on a scale holding 2 balloons. A large mouse crawls on its back. The reading on the scale was found to be 20,500 newtons. Determine the mass of the mouse. Okay, so we don't know the total mass anymore. We don't know what the total mass is times g. But they're standing on the scale. There are 2 balloons. So the force of the balloons is 2 times 200, which is 400 newtons. And there's because now we're back in a situation where we're touching the surface, and the scale reading is the normal force. Which is the normal force. And it equals 20,500 newtons. So this we don't know. So we look at this, we say, well, look at all this force pulling up. It's got to balance this because the net force is 0. It's balanced. So we write Fn minus the force of the balloons. And by minus, I mean plus. Less the weight equals 0. And we now have that to find, I'm just going to move this over. So it's Fn plus Fb equals mg. And we're going to find out what that mass is. So it's Fn plus Fb all over g. Okay, now what we do is just plug in some numbers. The normal force is a big 20,500. There was an upward force of 400 newtons from the balloons, and all divided by 9.8. So if we put that in our calculator, we say 20,500 plus 400 divided by 9.8 is about 2,133 kilograms. So the mouse was on top. This is both the mouse plus vector the elephant. So the mouse equals 2,133 less 1,000, which was the vector the elephant. It's got to be super dense. This mouse has more mass than that whole elephant, yet it's contained in this tiny little package here. So his density, he has this massive amount of mass and this tiny little volume, which makes no sense. But that's, I guess, how I made the question. It probably would have made more sense if the normal force only went up by like 10 newtons or something like that, not 10,500 newtons. In any case, you get the idea how to solve these problems. Be careful, like when the object's in an accelerated phase, then it's not touching anymore. There's no normal force. The normal force is only there during contact, and it's always perpendicular to the surface. What you're going to do now is work on the normal force problems worksheets. There's 9 questions, but don't do the elevator problems yet. You're going to learn how to do elevator problems later. There'll be a lesson associated with that. So do the questions from the normal force problems, and then there's a normal force assessment, which has 1 question, and a normal force warm-up, which has 2 questions. Do those as well. Okay, so those are the ones you'll see them listed on your work. All right. And that is a normal force.